Good afternoon, everyone. Welcome to the third webinar in a webinar series hosted by University of Chicago's Center for Translational Data Science. This series is to enable members of research community to help that they can use to advance data-driven scientific discovery. My name is Piyush Pandey, and I work as a project manager for Center for Translational Data Science. I will be moderating today's webinar and Q&A session. In this webinar, we'll talk about Gen3 data modeling with its services, Sheepdog and Peregrine. Today's webinar is presented by Chris Meyer. Chris is working as a scientific support analyst at Center for Translational Data Science. All the participants during the webinar will be muted by default. However, throughout Chris's presentation, if you have any questions, you can post it in the Q&A window. If you face any technical difficulty, please let us know in the chat window, which will be moderated by CTDS Project Manager Gina Kiffel. One last note before we begin, please bear in mind that today's webinar will be recorded. With that, I will hand things over to Chris.
Thank you, Piyush. I'm very excited to be presenting today, so I'm going to go ahead and share my slides. All right. So let's get started. I also wanted to mention, like Piyush said, this webinar is for your benefit. We want everyone to learn something new about our technology. It's not so much a lecture, but an interactive webinar. So we really do encourage you, if you've got any questions at all, to please go ahead and post those questions in the Q&A box, like Piyush said. The title of today's webinar is Gen3 Data Modeling, Herding Data Submissions, and Hunting Down Data. The outline for the talk is what is a data model, then the structure of a Gen3 data model in particular. Then we'll talk about herding data submissions, that is importing data and exporting data. Next we'll talk about hunting down data, that is querying and filtering the data. And then finally, we'll do a quick demonstration of query, export, and import features in the workspace. So jumping right in, what is a data model? In general, a data model organizes terms in a data dictionary and defines how they relate to one another. It is the implementation of a data dictionary and enables Gen3 services to submit and query data. The data dictionary, on the other hand, defines and describes how research data sets are represented in the database and harmonizes these terms from different data sources. Data harmonization is the foundation of the data commons concept of sharing data for cross-project analyses. In this paradigm, you take unharmonized data sets that are from different data sources, you harmonize those terms to construct a harmonized data dictionary. So what's the purpose of a data dictionary? They get everyone on the same page. The data dictionary defines nodes and properties used across different but similar projects in a process that we call data harmonization. The data dictionary helps avoid inconsistencies in data reporting and use across projects. They make finding data easier, subsetting and analysis easier by enforcing data standards, and they support mapping terms to external controlled vocabularies, like the NCIT or the National Cancer Institute's thesaurus. An example of a data dictionary harmonization task is on the right here. In this example, different studies may have their own unique term for the date a participant is enrolled in the clinical trial. Those terms can be harmonized or mapped to a single term in the data dictionary. So one study may call it an anchor date, another may call it an index date, and yet another may call it a date of enrollment. The data harmonization process settles on one single term and one definition for that term. And the data model enables the Gen3 services to import, export, and query data. Data import and export is accomplished by the Sheepdog service, which checks submissions against the data model to ensure all required fields are present and have appropriate values. Database queries are facilitated by the Peregrine, Arranger, and Guppy services. Queries must conform to the data model for successful data retrieval. So next I'm going to talk about a Gen3 data model, a little bit more in the details of what a Gen3 specific data model looks like. So a Gen3 data model is a graph-like relational model, and it consists of interrelated nodes that store certain properties. In the example shown below, there's a snapshot of a data dictionary showing the subject node, and below that, all of the properties that are stored in the subject node. On the right is an overview of an entire data model, and the boxes are the nodes in the data model, and those nodes are related to each other through links or edges, represented by the lines between the boxes. Structured data are imported and exported as key value pairs by the Sheepdog service. The data element keys are termed properties in Gen3. Property values can be queried using GraphQL, which is accomplished via the Peregrine, Arranger, and Guppy services. Sets of values in a node are called records or entities, and these are assigned unique IDs or universally unique identifiers. An example of that is seen on the bottom right. Here I'm querying the subject node, and I'm asking for the properties ID, which is the universally unique identifier for each subject record, and then the primary site and disease type properties. And you can see on the right, beside that query, is the data that's returned from the GraphQL API. It gives 2 records in this particular view, and you can see the IDs for those records are the 128-bit UUIDs. And it also returns the values for the properties that I asked for. Properties are organized into nodes, and a node is a category of structured data. Each node must have a relationship to at least one other node, and in Gen3, the root node is program, and that program node must have the project node as its first child. The data model is a JSON that's created from node schemas in the YAML format. Each node is defined in a single schema. The schema contains the following: a node ID, which is used for data queries and submission, a data category used to group nodes conceptually, a description of the node's contents, a list of links defining that node's relationship to other nodes, a list of required properties, and then finally a list of properties within that node. Property definitions include a property name, the description of the property, and a type. In Gen3, the types that are allowed are strings, which is any alphanumeric string, and enumeration, which is a type of string that only accepts particular values. On the right, you can see the example blood tube type. It's an enumeration, and it accepts EDTA, STREC, not applicable, unknown, etc. Integers are whole numbers. Numbers are floats or numbers with a decimal. Booleans accept a true value, true or false value, and an array is a list of strings. Notably, you can put limitations on the acceptable values for different properties. For example, integers and numbers can have a minimum and maximum. Strings can be limited by assigning them as enumerations, which are by their very nature limited strings. And then strings can also be required to match patterns. For example, as I mentioned before, the UUID, universally unique identifier, is a property. That property is in every node, and you can see that it must match a certain pattern. If you try to submit a record to a Gen3 Data Commons and it does not conform to the data model, that submission will fail. So now we'll get into specifically the submission service, which is Sheepdog. The Sheepdog service shepherds data submissions into the graph database. Sheepdog checks the validity of each record in a data upload against the data dictionary to ensure all required fields are present and have appropriate data values. Sheepdog also supports export of structured data records in the TSV and JSON formats. In a Gen3 Data Commons, there's 2 different basic types of data. There's data files, which must be downloaded to view their content. the content of a data file is not accessible via API queries. An example of a data file is an image, a spreadsheet of tabulated data, or DNA sequencing reads. That's in contrast to structured data, also known as metadata, which consists of records containing variable key value pairs, which can be queried and modified via the API or viewed in the Gen3 data exploration tools. Next, I'd like to talk to you about the steps for data import. Generally, this involves three phases. The first is authorizing users to upload data. The next is having those users upload data files. And then finally, submitting the structured data. The file upload process follows the linked data lake paradigm. Data files are uploaded to object storage, which is typically in the cloud, for example, an AWS S3 bucket or a Google Cloud bucket. And users don't necessarily see the bucket contents. So they don't know where their files live, but instead our IndexD service assigns each file a unique identifier called a GUID or GUID to each file. And users use these GUIDs to access files. The Gen3 data client is our command line tool for uploading and downloading data files. Briefly, the command is configured with your credentials, and it sends files to an S3 bucket or a bucket in the cloud. The unique GUID is minted for each file, and IndexD creates records linking the cloud location of files with the data file records in the data model. In more detail, the steps to upload files with the Gen3 client involve the following. First, you need to configure the Gen3 client with credentials that are downloaded from Windmill. The Gen3 client configure command takes three flags. It takes a profile name, you tell it the API endpoint of your data commons, and then you tell it the location of your credentials JSON that you downloaded from your profile in Windmill. Next, you can use the Gen3 client upload command to upload your files. You give it the profile that you just configured in the configure command, and you also give it the upload path, that is the path to your files. Notably, this supports regular expressions and wildcard characters. So you could, for example, say Gen3 client upload and give it the upload path star.fastq to upload all the fastq files in a directory. Or if you had a collection of directories, you could do star/star.txt, and that would search recursively through every directory for text files. The final step in file upload is mapping files to a node in the data model. First, you go to Windmill and click Submit Data, and then find the Map My Files button and click that. Next, you see a list of the files that you uploaded, and you check the checkbox next to each file that you're ready to map to a particular node. After that, you assign values to all the required properties for the files, and then finally, when you submit that, Sheepdog creates the structured data records for those files. Now that your files are uploaded and mapped to the data model, the rest of the project's structured data, that is metadata, must be submitted and linked to the data file records. Structured data is typically submitted node by node, and this is typically done using TSV files. Our data commons also supports data submissions in the JSON format, and we also offer an interactive form submission where you can type in the values for your records. The Sheepdog service then checks each submission against the data model to ensure it has the required properties and the appropriate values. And then if it's a successful submission and it matches the data model, the Sheepdog service creates one record for each row in the TSV or entity in a JSON. If you submit a previously created submitter ID or UUID, then the records are updated and the data that you submit overwrites the existing data if it's changed. In more detail, the TSV, or structured data submission process, follows the following workflow. First, you go to the data dictionary and download a template TSV for each desired node in your project. Next, you populate template TSVs with your structured data. And then you submit TSVs in the proper order. The proper order is top-down, starting with the root node and moving towards leaf nodes. Next, you update links in the data file TSV to link the files to their corresponding upstream structured data. Upon success, Sheepdog updates the data file records with that new link to the structured data, and your project is complete. As I mentioned before, during TSV submission, the Sheepdog service checks each entity or row in the TSV against the data dictionary. If any entity or row in the TSV is invalid with respect to the data model, your submission will fail. After fixing any errors, the submission should be successful and records should be created or updated by the Sheepdog service. As I mentioned before, you could submit a TSV and then resubmit that TSV having changed some of the values, and since the IDs and submitter IDs haven't changed, those records will be updated as opposed to created. Next, I'm going to talk about hunting data down, or querying and filtering the data in your database. First, I'd like to talk about Windmill's exploration page. Windmill's exploration page is a graphical user interface for cohort selection. Certain facets of the data are exposed for selecting cohorts. You can click in the GUI to select certain values for different properties, and it filters all the cases in the database based on that. Once you've selected a cohort based on the facets you selected, you can download a manifest that can be sent to your workspace or Jupyter Hub for easy data file access and analysis. Next, I'm going to talk about API queries for cohort building. This is accomplished by the Peregrine, Arranger, and Guppy services. If you click the Query button in the top navigation bar of the Gen3 Data Commons, it brings you to the graphical query building, interactive query building interface. This makes building queries more intuitive and supports both flat and graph model queries. We'll go a little bit more into detail about what the flat and graph models are, but graphical is neat because it has built-in documentation. It supports autocomplete for objects, fields, and arguments, and supports the ability to pass variables in your queries. As I mentioned before, the graphical page supports graph and flat model queries. These two different query types use different endpoints and query different databases. The graph model hits the Postgres database and has the following API endpoint. The flat model, on the other hand, hits the Elasticsearch database and has the following endpoint. The Peregrine service is the one that searches the Postgres database, as I mentioned. And Peregrine essentially is a service that translates GraphQL queries to SQL queries, and then retrieves the data and returns it to the user in the form of a JSON. The flat model, on the other hand, as I mentioned before, is queried via the Arranger and Guppy services, and these services hit the Elasticsearch database. The neat thing about Elasticsearch queries is that they support aggregations. And Guppy is one of our up-and-coming services. It's not released yet, but it's going to facilitate easier GraphQL-like queries of the Elasticsearch database. As I just mentioned, flat model queries support aggregations for strings and numeric fields. For strings, you get bin counts, or the number of records that have each key. An example of that is seen on the right. I'm asking for an aggregation of race in the subject node, and I get a bin or a document count for each different value for the race property. For numeric fields, on the other hand, you get summary statistics with an aggregation query. The summary statistics it gives you are the minimum, maximum, average, count, and sum. Notably, if you're not into GUIs, queries can be sent to both the flat and GraphQL API endpoints programmatically. Below, you see an example of using the Python request package to send the query to the GraphQL endpoint of the graph model endpoint, and you can see the data is returned in a JSON format that can be easily read in using Python tools. Next, I'd like to talk about data import and access in the Gen3 workspace. Specifically, we'll go over import, export, and query in the Gen3 workspace Jupyter Hub. Data can be exported programmatically, for example, in a Python notebook using the Gen3 SDK, which is our open source suite of functions for interacting with Gen3 APIs. You can import the Gen3 SDK in Python using import Gen3. The Gen3 SDK code lives in GitHub at the following repository location. Now, let's take a brief look at the Gen3 workspace, and we'll go over data query, data export, and import in the Jupyter Hub. So now I'm going to log in to the DCF Sandbox Data Commons. This is the landing page, and you can see up here the top navigation bar that I was talking about. Exploration takes you to the exploration page. Dictionary shows you the data dictionary. Query takes you to the graphical query building interface that I discussed. And then workspace takes you to our Jupyter Hub workspace. So now I'm going to run through a Python notebook that's going to demonstrate some of the things we talked about today. If you've never seen a Python notebook, basically it's an interactive way to run Python code. Code is entered in cells and is executed cell by cell, similar to the IPython shell in a terminal. Python notebooks also support Markdown. You can see here I've added comments in the Markdown language, the Markdown format. So we're going to go over, as I mentioned, query, export, and import in this Python notebook. So the first step is to install the Gen3 SDK. I'm doing that with pip, and I'm sending that command to the terminal using this exclamation command here, pip install Gen3. So we've successfully installed the Gen3 SDK, and now I'm going to look at the different classes and create instances or import the different modules from this SDK. And next, I'm going to set the API endpoint variable. That's going to point to the DCF Sandbox comments. And I'm going to initialize instances of the Gen3 SDK classes that we just imported. The endpoint, as I mentioned, is the URL of the comments you'd like to interact with. And refresh file should point to the location of the JSON containing the API keys you downloaded from the profile page. If you'd like to see that, essentially you click on Profile in the Data Commons, and it takes you to a place where you can click a button to create a new API key. Then you can download this key as a JSON, and then once you've downloaded the JSON, you can go to your workspace and use the upload button to upload that file. I've already done that, so what I'm doing is I'm telling the authentication class of the Gen3 SDK where that file is located, and I'm reading that in to the class instance. Okay, so first we're going to talk about querying structured data by sending API requests to the GraphQL endpoint. First we're going to import some more Python packages, JSON and pandas and JSON normalize. Next we're going to define the query we'd like to send to the API and save it as a text string. What this query is doing is it's requesting the following information from the DCF CCLE project, and that's specified here in this argument. I'm asking for the number of subjects in the project using subject count, the number of demographic records for those subjects using demographic count, and then I'm querying the demographic node. First 0 means give me all the records, not just the first 10, which is the default. And I'm specifying the project DCF CCLE, and I'm specifically asking from the demographic node, give me the gender, race, and ethnicity for every record. So I've just saved that query as a text file, as a text variable. And next we're going to send that query to the API endpoint using the Gen3 submission query function from the SDK. So here I'm just running that function. And we should see the JSON response soon enough. Here it is. So we get the counts. There are 1,046 records in each of these nodes. And you can see here are the values for each of those records that I asked for. For easier data analysis, we can convert that JSON to a pandas data frame using the pandas module. And we can see here I've described the data frame. We can count each value for the gender property, for example. We can do some plots using the matplotlib package. This is just a bar graph showing the number of female subjects and male subjects and the ones that have no designation for gender. So that's, in a nutshell, queries. Next, I'd like to talk about how you can use the Sheepdog service in Jupyter. First, I'm going to give an example of a data import. You can send data to the submission API, and Sheepdog will create records. So the first thing I'm going to do here is I've saved a record that I'd like to create in this string. I've given it, this is the study node, and I'm assigning particular values to these properties in the study node. I'm saving that as a JSON, and then I'm using the Gen3 SDK submit record function to send that record to the DCF demo project. You can see I got a code 200, which is a success code, and created entity count as 0 because I ran this already. You can see it updated the entity because it already existed. Next, I'm going to create a subject and link that's linked to that study I just created. The link is here. I'm saying that the subject with this name is going to be linked to the study node in the same way. Okay, that was also a success. And you can see it also updated because I already ran this code and created it previously. So next, we're going to talk about data export. The Sheepdog service also supports exporting all data from a node, and it can be exported in the TSV or JSON formats. The following code uses the Gen3 submission export node function to export a TSV of all the data from the summary drug response node in the project DCF CCLE. This export is handled by the Sheepdog service and will finally read the exported TSV file into Python as a data frame. And it may take a minute because there's a lot of data. All right, here it is. So I've exported the node, all the data from that node, and I've read it into a data frame, and here's that data frame. You can see it's all the data. This is an alternative to queries. So I got all of the data instead of just the variables I asked for. And now I just have a couple of examples of showing how you can use that data. First, I'm going to make a table of the EC50, mean and standard deviation, for each compound. And we can make box plots for each compound using the matplotlib package. Or we can make a density plot of the EC50 for a single compound using the Seaborn package. And now I'd like to briefly talk about data file upload and download, which, as I mentioned before, is accomplished using the Gen3 client. The first step in that is downloading the latest version of the client from its GitHub repository. So I'm going to use the curl command to download the latest version. I'm going to unzip the client once it's downloaded. I'm going to make a directory .gen3, in my home, in my root directory of my VM that I'm working in. I'm going to move the client to that directory, and then I'm going to remove the zip file. I've ran this already, so it's telling me that that file already exists. Next, I'm going to configure the client profile using the same credentials JSON that I used to authorize using the Gen3 SDK. Now I'm going to use those same credentials with the Gen3 client. So I've given it the API endpoint, a profile name, and then the location of my credentials. And I'm running a command. Client here is the location of the Gen3 client. And I'm telling it to configure a profile with this API endpoint with these credentials. And it's done that. And now that we've configured a profile, we can use the Gen3 client upload command to upload a file to the data commons. I've preloaded a file here. It's not a real file. I've got to re-log in here real quick. So the file I'm going to upload is this demo reads_1 fastq, which I can look at. This is a fake fastq file. It's not a real file, just for demonstration purposes. So the command I'm going to send is Gen3 client upload. I tell it my profile, which has my credentials and the API endpoint already configured in it. And then I give it the upload path. And that path is going to equal that file name. Or I could also do, for example, *fastq. And here's the output. So it looks for all file paths matching *fastq, and it found the following files in that path, and it found my file. And then it uploaded the file, or no. Yeah, just because I already ran this command, it found it in my local submission history, so it skipped this file to prevent duplicate submissions. But if I had not already run this, it would say success here. And now, now I have a GUID for that file. It exists in the index, so I can use the Gen3 client download command to download the file. First, I'm going to run a GraphQL query to get the file's GUID by specifying the file name we want to download. I can do that with the following query. I query the data node, and I say, give me the files where the file name equals demo reads1 fastq. Give me the object ID, which is the data GUID, the file name and the file size, just to confirm that we're getting the right file. And then I'm sending that query the same way we sent previous queries. And the response should have the object ID of the file we just uploaded. So the last thing I wanted to show you is we're going to use the Gen3 client download command to download that file using its object ID. So I'm saving the object ID in this variable from the API response we got here. I'm configuring a new command, a Gen3 client command. It's a download command. I tell it my profile. It's got my credentials and the API endpoint saved in it. And I'm telling it the data file GUID. So let's see what happens. Hopefully it works. OK. So yeah, it just says downloading the GUID, successfully downloaded the file. And that concludes the tutorial. So I'm going to go back to the presentation briefly and talk to you about some future Gen3 services we have up and coming. As I mentioned before, arranger queries and Guppy both hit the flat model endpoint. That's your Elasticsearch database. Over on the far right is an example of an arranger query. You can see I've got to say hits, total, edges, and it's a little bit of a difficult language for people to learn if they're just dabbling and querying or just trying to use it to get the data they want. They don't want to learn a whole new language. So we're trying to make this easier by implementing a new service called Guppy, which provides simple GraphQL schema to explore the flat model. It does everything a ranger does and more. It can create histograms with bin aggregations for numbers. There's no limit on the results that you get returned, and you can give it JSON-based filters. And very neat thing for the future is that we're also going to support SQL syntax for filters. So if you know the SQL language and you don't want to learn GraphQL, we'll support that. Another neat thing that's up and coming in Gen 3 is the PFB format for exporting and importing clinical data to a commons. And this is going to be very useful, for example, to import data into a commons that has a different data model, because the PFB will have a copy of the data model in it with references to external vocabularies so that you can map terms from one dictionary to another. The PFB format is named Portable Format for Biomedical Data. Thank you for listening to the webinar today. If you'd like to learn more about Gen 3 and our organization's Center for Translational Data Science, you can visit our organization's GitHub account at UC CEDIS. You can visit gen3.org, where we have lots of great information about the Gen 3 technology. We encourage you, especially if you plan on using Gen 3 yourself or contributing to the code, to join our Slack community. We have a support email, that's support@datacommons.io, so feel free to send an email if you've got any questions as well. And finally, you can learn more about the Center for Translational Data Science, which is a department of UChicago at ctds.uchicago.edu. We'd like to thank our sponsors, like the National Cancer Institute, and highlight a few of our data commons, like the NIAID Data Hub, Kids First, Pediatric Cancer Data Commons, and the Brain Commons. And I'd also like to announce our next webinar. Please join us on Thursday, June 13th at 1 p.m. for a little bit more of a deep dive into using Jupyter Notebooks to do data science with Gen 3. And with that, I'd like to move on to the Q&A portion of the webinar.
Thank you, Chris. At this point, we will address questions that have been submitted so far. If you haven't, please submit your question by clicking on Q&A button. Joining us for Q&A session is CTDS Director for Environmental Science, Zach Plummet. Welcome, Zach.
Hello.
So I'll start with the questions that have been submitted. So the first question is, for structured data updates, are the historical values stored in the graph somewhere?
You want to take that one? Do you know the answer? Okay, so for when you're updating in the graph, we do keep the transaction logs, and then Gen 3 also has a concept called voided nodes, which we don't make heavy use of right now, but that does keep more of the information about the versions of the values in there. Sort of moving forward, the way we'll do this is actually with the PFB that Chris was just mentioning. And so with PFB, since you're actually able to store the dump of the entire project or the entire commons as a serialized file, we'll basically be able to version that just sort of like a standard file on S3.
Oh, thank you, Zach. So I'll move on to the next question, which is link to doc for aggregation query. So I guess, where is the link to doc for aggregation query?
If you visit gen3.org and then look in, I believe, the developer section, and under resources, you can find more information about documentation on aggregator queries, ranger queries. There's also, like I mentioned, in the graphical interface, there's built-in documentation, and it also supports autocomplete, so it can help you learn how to build those queries if you don't already know how.
Thanks, Chris. So the next question is, how are DCF credentials.json populated into the notebook user's home directory?
Right. So it's very simple. Jupyter Hub, which is what I was showing you, has an upload button. where you can click that and then just browse your computer for a file to upload. So that's one way of doing it. I believe it also supports drag and drop. So you can just find the file on your computer that you downloaded from Windmill and then drag that credentials JSON to the folder that you'd like.
I think Brian Nix mentioned that that has already been answered, but still, thank you, Chris.
Sure.
Next question reads, are there TSV JSON files for the DBC, I guess DCF, maybe CCLE project we can download and use locally in our Gen3 instance?
Yes, so as I mentioned before, the SDK has functions for exporting all the data in TSV or JSON format. You have to have access to that particular project. You have to have read access in order to download that data. But if you have read access to that project, you can use the SDK, as I mentioned before, just to download all the file, all the information from that project from each node.
Okay, great, thank you, Chris. Next question reads, I would assume that the user needs to create a submitter ID for uniqueness of the node. This seems to be a bit of a burden for the end user, and he feels that should be handled by the system.
So the general stance with Gen3 is that the submitter ID is really where the user would put sort of their identifier for the actual the case or the node or the record, basically. And so most people already have these identifiers, and so it's not too much of a burden because this data is typically being tracked elsewhere outside of Gen3. So you would just reuse that identifier. You don't have to create a new one.
Okay. Thank you, Zach. So I'm going to read next question, which says, what happens when you want to make modifications to the model? Example, add a new node, create a new relationship. How does it impact the system? The Postgres and or Elasticsearch? Is it a full re-indexing or partial?
So it depends on whether or not the change that you've made invalidates the data that's already in the database. So we subdivide dictionary changes into breaking changes and non-breaking changes. So a breaking change would be any change that invalidates something that's already in the database, like changing a node name. That would invalidate anything submitted to that node, in which case you would need to, before you made that change, make sure you've backed up the data, and then make the dictionary change, and then you can resubmit the data after that. On the other hand, adding a new node that didn't exist before, as long as you're not invalidating any edges or links between nodes, but instead you're just adding it as a leaf, that is non-breaking change, or adding a new variable to a node is always a non-breaking change. And in those cases, you can update the dictionary on the fly.
Thank you, Chris. Next question reads, if multiple files are loaded and if there are errors, partial upload duplicate, is it an all or nothing upload process or a file-oriented response when using the Gen3 client? That, Chris?
Sure. So it sort of depends on the actual case, right? So we utilize some what we call trunking on the front end right now. And so if you are actually submitting more records than the number that's supported in single chunk, then you can have cases where you actually only upload part of your file. And so we're working on sort of correcting that as we go forward. And so in the future, it'll always be treated as sort of all or nothing. And then we're also improving the error handling that you see. And so we're trying to make the errors more visible and give you more information on what actually went wrong so that it's a quicker turnaround to be able to fix it. When you're using the Gen3 client to do the upload for the files there, you will, if the file gets fully uploaded, it's there. If something goes wrong, then of course it's not. And you can, then when you're using the Gen3 client, you can then resume those uploads as well.
Okay, thank you, Zach. Next question reads, is it possible to upload the nodes and relationships separately right now? And if not, is it in the pipeline like in a true graph-based system?
No, it's not possible to upload the nodes and the relationships separately right now. So one of the things here is that you do have to have all of the data that you want to link to already uploaded. And then when you're uploading sort of the downstream node, you have to specify the links, of course, there as well. And that's just to make it so that we're making sure that the users are actually putting good data into the system. It wouldn't make a whole lot of sense for them to want to upload a bunch of downstream nodes and then not link it to the actual case. That sort of breaks the entire model for how access controls and things like that work.
Thank you, Zach. Moving on to next question, which says, if an upload fails, is a report generated with notes on how the upload failed? Specifically, which column row caused the failure?
Yes, so we already do provide some of that information, and as I mentioned in the answer to the previous question, we're working on improving that as well, so that the reports are more clear on exactly what failed and exactly how you might be able to go about fixing it.
Okay, thank you, Zach. So I'll move on to the last question, though Chris has already talked about these future services, but still, what I just want to have that reiterated, that what new things can people expect when it comes to Sheepdog and Peregrine we talked about today.
Right, so we talked about Guppy, which is an improvement of the flat model search. And we also talked about the portable format for biomedical data, which was going to make importing data and exporting data a simpler process.
Okay, thank you, Chris. Thank you, Chris and Zach, for the questions. Those were the questions that we had. So now, once the webinar ends, you will be prompted to complete a feedback survey form. Later, we'll share a recording of Chris' presentation with a link to register for next webinar, which is scheduled for June 13th. In that webinar, we'll talk about data science in Gen3 through Jupyter Notebook and other apps, how they are used with Gen3. If you have any remaining questions about today's webinar, Gen3 software, or UChicago's Center for Translational Data Science, you can reach out to us via gen3.org or ctds.uchicago.edu. This concludes today's webinar. Thank you again for participating. We'll see you on June 30th.